So, welcome folks. I'm Matt Jarvis. I'm a senior developer advocate at Snyk, and I'm joined today by my colleague Camille Potrek, who's a senior security engineer at Snyk.
Hello.
So, today's talk is going to be about kernels. So let's start with making sure that we have a shared understanding of what a kernel is. We're going to be pretty generalized here because there are a variety of different ways that these things work, but it's definitely not either one of these. So when we talk about operating systems, we're describing the core software that provides the interface between the computer hardware and the end user. And whilst operating systems may ship with end user applications in them, like Windows or Mac OS, in the computer science sense, we're talking about the programs that enable applications to run on the hardware. And this would usually consist of the operating system kernel and various utilities and libraries that perform the base functions of operating the computer. And the kernel is right at the heart of this. It's the first thing that's loaded by the bootloader when we start the computer, and it's always resident in memory. The function of the kernel in general is to handle interactions between software and hardware. So everything from managing the CPU, reading and writing from disk, and handling packets on the network. And this is a little old diagram, but fundamentally, this is how the boot process works in a Linux system. And the BIOS is firmware, so that's software that lives in the hardware and that lives on the motherboard. And it's the first thing executed by the CPU when the CPU is powered on. The BIOS then looks on the various disks that might be configured, looking for a master boot record, an MBR. And if it finds a partition labeled bootable in the MBR, then it'll load the boot sector code from that partition. In this case, it's a bootloader grub. And then the bootloader will then load the kernel. And once the kernel's running, it'll load what's called an initialization daemon, which then handles all the starting of other system software, and the system is then up and running. In modern Linux systems, the init is usually systemd. But this is the kind of a typical pattern of operation. So if all of our applications access the hardware directly, you can imagine that things would get pretty complicated, and the potential for things to go wrong would be huge. While some historical computers used to work like this, in general, they ran single applications, so there wasn't that much of a need to manage access. So in this way, the kernel acts like a traffic controller, directing requests down to the hardware in the right order, synchronizing actions and keeping the flow of information happening all the time. And modern operating systems are multitasking. That means that the CPU switches between applications to keep them all running all of the time. And the CPU is only ever really executing one thing, but it happens so fast, this switching, that it's invisible to the end user. So it looks seamless to us when it's happening. And what actually happens is that as each process needs time from the CPU or to interact with something, the kernel basically saves the program state into these process control box PCBs, switches process, executes what it needs to, saves that process's state into another PCB, and then switches back to the original process, reloading its state from that PCB and so on. And operating systems in general separate their memory into kernel space, which contains the kernel and things like device drivers, and user space that contains all of the other running applications. The processor prevents applications from accessing kernel space or each other's memory. And this is the basis for memory protection, for stopping programs from stomping all over each other. This also enables privilege separation, so allowing different things to have different permissions to do things inside the operating system. In general, applications don't talk directly to the kernel. Instead, the kernel provides an abstraction layer for applications to access, known as syscalls. And these provide an interface for applications to ask for things like writing to the disk, sending packets over the network. And when an application performs a syscall, the CPU will make the switch from user space to kernel space. And this mechanism is known as context switching. And the kernel will then execute that syscall, and the CPU will switch back to user space, returning any data to the application that was a result of that syscall. And every time the kernel does this, it needs to check if the process that's asking to do it is actually allowed to perform that action. Behind the scenes, the kernel maintains a list of processes together with a set of allowed capabilities or permissions that the process has. This is represented in the kernel as this data structure called struct task struct, which looks like a bit like this. And this structure contains a ton of information about the process, including its PID, its JID, and the priorities it should be allocated. And it also contains references to these credentials data structures, which are the ones which set what things the process is allowed to do. And this is defined in the kernel headers, and it defines a whole set of capabilities, these kernel level permissions, which the process is allowed to execute. And there are various sets of these capabilities defined in the kernel, which sort of depend on how the process is launched, but fundamentally they're all defined in this data structure. So every time the process asks to perform a syscall, the kernel will look up this structure and check if the process is allowed to do it. So over to you, Camille.
Okay, thank you. So now we can describe what privilege escalation is. In short, it's the process of obtaining more permissions than we currently hold. As Matt explained, in Linux kernel, these credentials are stored in the task struct, which then points to credentials struct. Our goal in this exploitation exercise will be to change the UID and group ID from any value to 0. 0 represents the root permissions on a Linux system. First step in our process is to identify a vulnerability. These are examples of some vulnerabilities that happened in the past that led to a privilege escalation exploits. As you can see, these occur more or less once a year. These are some of the websites where you can find proof of concepts for these vulnerabilities and see how the code looks like in real life. So once we know that there is a vulnerability, we need to be able to reach it. In kernel, we can do that by trying to execute a system call, which then enters into kernel space. Remotely, we can trigger that by sending network packets to the machine, which then going to be processed by the kernel as a first place. And we can also do that via the BPF programs, which are loaded into the kernel and execute code in that memory space. If we go to the next slide. Once we reach vulnerability, we need to be able to control it. There is multiple capabilities in a kernel developed specifically to trump some of these vulnerabilities. SMAP and SMAP will prevent execution of certain memory location or even accessing that memory if specific conditions are not met. Address layer randomization will change locations of certain functions within the kernel to prevent you from finding out and executing them. Page table isolation separates memory pages from being accessible in certain regions. So for example, when you're in a kernel space, you should not be able to see user page tables, which prevents you to do some of these exploits. Next, we also have kernel is a complex state machine. It's got a scheduler. It's got a memory system that does a lot of operations very quickly. All of these operations can change memory layout and cause our exploits to misbehave. And finally, the last thing we need to be able to do is to return the control of our exploits back to the user. When we're exploiting these issues in the kernel, we need to be able to send some sort of signal to the user so that they can take control and execute further actions. In local execution, this means usually spawning a shell, a control terminal for the user. In remote exploitation, this means sending packets to remote system, usually called control systems, so that they can send more instructions from the attacker. If we go next. Okay, so in our demonstration, what we have set up, we have a Kubernetes cluster deployed with kubespray and Ansible. Our worker nodes are running a Ubuntu system, and we're still using Docker as our container runtime. So we all are familiar with concept of pods. Pods run one or more containers. However, in a Linux space, there is no construct of container. To the Linux kernel, containers are simply processes that are then controlled with control groups, namespaces, and capabilities to form a abstract container layer, which is pretty much a sandbox for the normal user. We go next. In our example, we will be using a old vulnerability from 2017. This has been patched a long time ago, but we have reverted some patches in the kernel to reintroduce this. The vulnerability itself is a signedness issue, but when exploited, it leads to out-of-bound heap write, which allows us to control some memory locations in the kernel. By default, this vulnerability is not really reachable by normal Linux user, because in order to do that, we need to be able to send raw packets, and that requires a net admin capabilities. However, in most Linux distributions, the user namespaces allow unprivileged users to create this kind of sandbox environment where they gain additional privileges, which allows us to reach this kernel system call. The privilege escalation in the kernel usually involves setting the credentials struct with a value 0. This pattern of system calls allows us to perform this quite easily once we have executable writes in the kernel. So commit kernel creds and prepare kernel creds is a common pattern when we see privilege escalation. So in our first demo, what we're going to see is how the exploit behaves on a normal standard Linux operating system. This is a Ubuntu system. This doesn't involve any containers. This is just a host. As you can see, we are user 1000. We have placed a flag on the system to showcase that it's not readable by our current user. As you can see, it's a permission denied error because it's only readable by the root user. We're going to trigger our exploits. It runs quite quickly. But what you can see now is that we have root permissions and we can access the flag on the system. So we've gained additional permissions by exploiting vulnerability in the system. Right. Okay, so for the next thing, what are we going to do? We're going to trigger the same exploit in the Kubernetes cluster. What we have here, we have configured a pod with some security restrictions. So we're specifying that our pod will be running with user 1000. We explicitly prevent it from gaining more privileges within the container. And we also dropping all the capabilities to showcase how this exploit works in more hardened pod. We're going to see the pod spec again, just to show that we're using the correct configuration. In order to prove that we have root permissions, we're also mounting the flags within the container. We're going to execute a bash shell inside of the container. We're checking again what is our user ID. It's 1000. We're going to show that on our root file system, we've mounted a flag that is only readable by the root user. We prove that we cannot access the contents. We're going to now execute the exploit code again within the container. As you can see, we've obtained again root permissions. We can now read the flag within the system. we're gonna show that the flag has permissions, but what we cannot see is the host's IP addresses on the system. We're gonna explain in a second why that is. So in order to understand why we didn't see any network interfaces, we need to introduce concept of Linux namespaces. These are Linux namespaces, not the Kubernetes namespaces. In Linux, there are 8 namespaces. We're only going to cover 4, which are most important to our system. So first, user namespaces are responsible for isolating the IDs and user attributes that relate to credentials. Network namespaces isolate network resources, that being network interfaces, ports that you can see attached to the processes. Process namespaces isolate the tree of the process view. In space of containers, what that allows us to do is to have unique view of the processes that appear to be running within the process. And finally, mount namespaces are there to separate storage and file system permissions. That allows us to create a unique view of the file system within the container. The namespaces are also represented within the cred struct. These are called user and user-ns struct. So in our exploit example, our next goal is to overwrite these pointers so that we can restore the root host's namespaces in the system. In order to do that, we need to expand our exploit code to introduce new system calls. Now we need to identify what is the host's namespace ID and pointer, and override these with our current process. You can find these under the proc file system, and therefore these system calls will allow you to identify and replace them. So our take 2 improves on our exploit by adding this step to restore the host namespaces in order to gain more privilege within our container. So let's see how this works in action. What we have here is we're going to reuse the same pod that we used before. We're showing that on a host, we've placed 2 files, flag and container flag.txt. We cannot access it from the hosts because we don't have the permissions. We're now going to execute a bash shell within our pod again. We're going to see that on a file system within the host, we only see one file now, so we're definitely in a container. We're going to run our improved exploit. And what we can see now is that we have root permissions, but when we list files on the file system, we see more files. We see not only both flags, but we also see the boot images that belong to the host. We can read these files from the container. We can also see all of the network interfaces that belong to the node. And we can also see all the processes that are running on the node, including privileged processes like Calico. In order to prevent some of these exploits, Kubernetes exposes some security controls that are linked to the Linux controls. One of those are capabilities. We can drop almost all process capabilities by specifying security context capabilities flag. Unfortunately, for some exploits, that is not enough. In our example, we've shown that dropping all capabilities didn't prevent us from reaching the vulnerability. That is because capabilities do not always cover all system calls within the Linux kernel. The second security control that we can implement is Seccomp. Seccomp is a filtering system that filters out system calls that are preventable. By default, on Kubernetes, Seccomp runs with unlimited filter list, which means you can execute any system calls you want, but you can specify security context to add a default filter, which will prevent some of these exploits. And as you can see in a second, it helps in preventing the exploit that we have created. And finally, we can also apply Selinux or Apparmor profiles to our containers. These are mandatory control systems in Linux, which work as additional layer to prevent access between different processes. That can also prevent some of the exploit, even if you obtain root permissions on the system. So for the next scenario, we're gonna introduce a Seccomp profile to our pod. We're running all the version of Kubernetes, which means we need to do that by annotations. And let's see how our exploit behaves when we apply a Seccomp profile.
Sorry.
So what we're going to see is the pod spec for the new, more secure pod. We can see that we're applying a default Seccomp profile. We can see that the pod is already running. We're going to execute a bash shell within that pod again. We can see that we use a 1000 again. We do not have permission to obtain access to our flag. We're going to execute the exploit. However, what we can see is that we receive a operation not permitted issue. This happens because the Seccomp profile prevented us from executing clone new user system call, which in turn prevented us from obtaining additional permissions and exploiting the system. So what else can we do in order to prevent vulnerabilities? We always have to patch our systems. The mitigations that we've shown in this demo are only as stopgap solutions. Always update your kernels when new vulnerabilities appear. Treat your pods as cattle, not as pets. That means do not try to keep them running as long as possible, and write your application so that you can rotate these pods as many times as you want. And finally, start preventing access to bash and interactive shells within the pods. This should be immutable containers, and things like distroless containers can prevent this exploit by not allowing some of these functions to execute. So what else can we do except containers? There are additional features that can be deployed. Kata containers and Firecracker introduced lightweight VMs as a runtime construct instead of using just bare containers. This means that each pod runs its own kernel, and in turn, any exploits cannot escape into the node because they only apply to the pod. gvisor is additional. It's a different technology that attempts to provide you with the same capabilities, but instead of creating light VMs, it introduces kind of a middle layer between you and the kernel, and it simulates some of the system calls, which gives you additional controls.
Yeah, I think this is me, Camille. So
all right.
As we've seen, these kernel level exploits are pretty powerful and have the potential to escape our containerization. The only real weapon, as Camille said, we have against this is to upgrade our kernels and to make sure we're using Linux security modules implementations like Selinux or Apparmor. Luckily, this type of vulnerability is fairly rare in comparison with more common application level vulnerabilities. And security context settings in our Kubernetes configuration provide us with settings which can reduce the blast radius if our containers do get attacked. So these principles of not running your containers as root, disallowing privilege escalation, and always following the principle of least privilege, like start with disallowing everything and then work your way back to finding the minimum set of capabilities that your application requires. And tools like Sneak can help here by scanning your Kubernetes YAML files and detecting those insecure settings before your containers are deployed to production. So thank you for listening. You can sign up for a free Snyk account at snyk.io/signup.